In a world of madness and chaos, in a workshop full of clutter, can there be any hope when a small part is dropped?
No. No, the answer is no. There's no hope at all. It's gone. Forget about it. Start over. Hey everyone, welcome back to The Boring Head. In the last episode, we made the major components, and now we just have a lot of fiddly setup work left to make them work properly. In this old stare-it box, there's an HA-low test indicator that reads in 10 thousandths. I found this at an estate sale a couple of years ago, and I like getting it out and using it whenever I have an excuse. The next operation will be machining the fixed gib. What I mean by fixed gib is that much of the material around one side of the female dovetail will be machined away, leaving a little bit so that remaining portion can sort of pivot on a spring. I don't think I'm describing it very well, but you'll see as we go along here. In order to do this, I need to set up the top half of the boring head that has the female dovetail so that the dovetail is running perpendicular to the axis of the mill spindle. The most convenient way for me to hold the part for this operation is in a V-block. Now really, I could have just set this up and eyeballed it in the mill, just using something in the spindle as a point of reference as the work was moved underneath it to get it close enough, because this really doesn't require a great deal of accuracy. But just for the heck of it, I set up this arrangement you see here that is totally overkill. It's a 1-2-3 block and a parallel to keep the height gauge a fixed distance away from the work, and that lets the test indicator run against the inside of the dovetails to give a reading of how square the dovetail is to the plane of the surface plate that this whole arrangement is sitting on. It's within about a 1/2 thousandth. That's more than adequate enough for this application. Now transferring this setup to the mill, you can see I'm using a slitting saw to slice along one side of the dovetail to start forming our, I guess you'd call it relief for the fixed gib. I've never had much luck with slitting saws making multiple passes. They always seem to run off the original course and leave a pretty horrendous looking surface afterwards. So I'm taking a full depth pass here. Now, unlike this old Tony, I can't afford time travel. So instead of traveling forward in time and using the boring head that I'm building to build the boring head, I had to resort to using the one I mentioned that I had already built some time ago that uses the 1/8 inch round tooling. This setup is to cut some additional relief on the inside corner of the dovetail for the fixed gib. Now, while we've got the work set up in the V-block like this, it's also a good time to drill and tap the holes for the gib screws. The holes are being tapped to number 540. An old razor blade worked pretty well to clear out the chips that got all packed up inside of the slot. Now we have a few more operations that require us to get this chucked back up into the lathe, and I've got it in a 4-jaw chuck, dialed in using that reference surface that I cut last time, if you remember, that is concentric with the shank. The brass nut for the adjusting screw will be a press fit in the top half of the boring head, so we're going to start out by drilling all the way through, and then reaming partially through that hole for a good tight fit with the brass nut that we will make later. The reason I'm drilling all the way through first is to allow access to the backside of the brass nut, just in case it ever needs to be removed in the future. Be extremely careful if you try this technique of supporting and driving the reamer using a tailstock center. If you're not real careful and if the reamer starts to pull away from the tailstock center, really bad things can happen. You can end up with the reamer flying all over the place. This is a very accurate way to hold the reamer if you don't have a floating reamer holder for your tailstock, but it does require some extra care and diligence. Lastly, we'll temporarily reassemble the boring head and just take a skim cut over the whole surface. For the brass adjusting screw nut, I used some brass hex bar stock that I had hanging around the shop. It was a convenient size. The only machining required for this was just to turn down one end to be a press fit with that hole that we just reamed a moment ago. The length of the nut isn't critical, but it's important that it's at least long enough so that there's room for a threaded hole to go through it, and short enough so that it still fits within the relief groove that we milled in the bottom half of the boring head. Before machining the adjustment features, the work needs to be set up in the mill with the dovetails parallel with the Z-axis, the spindle. The idea here now is to reassemble the boring head with everything set up in the mill like this, and drill straight through the lower half of the boring head and the brass nut that's pressed into the upper half. It quickly became obvious that the pressure from drilling was going to cause the two halves of the boring head to shift a little bit, so I placed a machinist square underneath just to keep it from moving. After drilling, the hole was counterbored to leave a surface for the head of the adjusting screw, the dial if you will, to sit down into. With the body of the boring head drilled and counterbored, the lower half is removed without disturbing the rest of the setup, so that the brass nut can be drilled and tapped. The adjusting screw threads are number 540. The only thing now keeping us from having a functioning adjusting mechanism is something to retain the adjusting screw, so that adjusting in one direction the screw doesn't simply back out. Here you can see a hole location laid out where we can place something to retain the adjusting screw. The retaining pin for the adjusting screw will itself be a screw. Having it offset to one side like this will reduce the tendency for the retaining screw to back out as the adjusting screw is turned. Instead of friction between the retaining pin wanting to rotate the screw, that friction will want to push up or pull down on the screw. This setup in the mill keeps the adjusting screw seated in the lower part of the boring head so that the retaining screw hole can be drilled into the boring head and all the way through the shoulder of the adjusting screw at the very outside edge. This feature drilled through the shoulder then acts as a guide for turning a groove all the way around the adjusting screw shoulder. With the screw removed, I'll go back and counterbore and tap the hole with number 172 threads. Now we get to play around on the watchmaker's lathe a little bit. We'll start by turning a groove in the adjusting screw shoulder for the retaining screw to engage with. Next up, the retaining screw itself. Now the screw is reversed in a collet to face and turn the head to diameter. The screw is reversed again so that the excess threads can be turned off and a pin can be turned on the end of the screw. The screw is reversed one last time to turn the head to its final thickness and to slot the head. This is one of my favorite techniques for slotting screw heads. Just a grooving tool held sideways in the tool post, set on center, and using the cross slide sort of like a shaper. Here I'm using a die just to clean up the threads after machining. We'll come back to that little screw later, but right now we're going to get started making the graduated ring for the adjusting screw. Instead of changing tools and parting off, I decided just to hacksaw it off in the vise. With the ring pressed onto the adjusting screw and faced to the correct thickness, the rest of the work will be done in the watchmaker's lathe. We'll start by turning a beveled surface that will receive the graduations. My set of indexing plates for the watchmaker's lathe doesn't include any counts that are evenly divisible by 25, and I need 25 graduations around this graduated ring. So I'm resorting once again to the computer-generated paper printout. Witness here how I've cleverly marked every fifth position so that every fifth index mark around the ring can be longer. Witness also how I'm a complete moron and marked the short lines from the wrong side of the dial. So I had to go back over them again and make them the full length, resulting in no difference at all between any of the index marks. Yep, here we are, the walk of shame, going back over all of them. I'm not showing it here, but to remove the burrs I just hit it with a fine file real quick in the lathe. And later on I used a little bit of black permanent marker to fill in the markings. Alright, let's get back to that tiny screw that we made. It was made from 01 drill rod so that it could be hardened and tempered. And it was during the tempering process that something went pretty wrong. Before we get to that, I'll take you through the process after hardening, but before the screw was polished. What you see here is my homemade screwhead polishing tool. It takes the same Webster Whitcomb collets that my watchmaker's lathe does. I'm starting off using a strip of 2000 grit abrasive paper with a little bit of oil on it. Next, I'm using some aluminum oxide powder. This is mixed with a very small amount of oil to form a paste, and here I'm using that paste on a strip of plain printer paper. If I was going for a perfect black polish, I would be using successively finer grades of this polishing powder, and as a last stage it would be used directly on a glass sheet rather than on paper. That purple stuff you see there is just some used acetone. That blob of green stuff you may have noticed me using is a sticky putty called Rodico. It's not watch grade, but it's a pretty nice finish, and with it thoroughly cleaned, we're ready to start tempering. My big mistake here can be traced back to my decision to use this little bluing pan for the screw, even though it was really too big to fit in the largest hole. As a result, I spent longer looking for the dropped screw and not finding it than it ended up taking me to make another one from scratch anyways. Keep your workshop clean, kids. Don't be like me. Through the magic of video editing, here's another screw, hardened and polished and ready for tempering. This time I took the insert out of my convertible bluing pan and filled it with table salt. I typically use brass chips, but have heard that salt works pretty well, so I wanted to give it a try. The only machining left is for tool holding. So the holes to take the actual tools themselves, and the set screw holes. I'm going to quickly show drilling and reaming one of the 3/16 inch boring bar holes. Note the high-tech blue tape for controlling the drilling depth. Showing the final assembly is a pretty good way for you guys to see the finished parts. All of the Gib screws have 1/8 inch ball bearings underneath them. The eagle-eyed among you might notice that I'm using a Torx driver for these little hex set screws. A T7 Torx driver with just a little bit of careful stoning is a fantastic fit in these number 540 grub screws. I didn't show milling the radius relief in the end of the boring head, but there was really nothing exotic there. Just rough milling followed by a ball-nosed end mill to leave that nice radiused edge. The finish on the body of the tool was applied with a pivot file. It was a total experiment, and I'm still not completely sure about it. It looks alright, better in person than on video and in pictures. The good news is that it will polish up pretty easily if it turns out Justin doesn't like it. There's just one thing left, and we need to take care of it pronto. Thanks for watching, everyone.